Hello, namaste, good morning, good afternoon, and good evening. Well, it's late evening here in Nepal, and we are starting at 7 p.m., that is GMT plus 5:45. Hope you all are doing good. This is Suraj Gautam, a civil engineer and DRR professional from Institute of Himalayan Risk Reduction, and I'll be your host for today's session. First of all, I'd like to welcome you all to our second episode of a webinar series on Geo-Science for Sustainable Development, which is being organized on a regular basis. In this webinar series, we'll be hearing the insights and amazing experiences, followed by some healthy discussions from our geoscientists. We had discussions on where did the India-Eurasia collision take place on our first episode of webinar series by Dr. Upender Baral. Our registrants and participants thoroughly enjoyed the session, and we have had a very interesting responses. And today, we'll be discussing on how Mantle Dynamics guided the main phases of Himalayan Crustal Tectonics. So on behalf of the organizing team, we are really grateful to our guest speaker, Dr. Alexander Webb, who will be sharing us with his insights and healthy experiences. So we would like to warmly welcome our speaker, Dr. Alexander Webb, who is an associate professor of the University of Hong Kong, Chinese Academy of Sciences, China. The session will be moderated by Assistant Professor Dr. Basantaraj Adhikari from Institute of Engineering, Tribhuvan University, who is also the visiting scientist of Institute of Himalayan Risk Reduction. Well, it is indeed an honor to have insights from our distinguished speaker. So we would like to welcome you all and our distinguished guests who are attending this session. We are very pleased to say that we have received amazing responses for this webinar. We had more than 200 registrations on the very first day of release of our webinar. And till date, we have more than 379 registrations throughout the globe. So to address this request, we are going live on our social media page of Institute of Himalayan Risk Reduction, we will be receiving the queries and feedback from our Zoom chat box as well as from our social media live stream. So before starting our series for today, I'd like to give a brief introduction about Institute of Himalayan Risk Reduction. Well, it's a research institute established with an objective to assess and understand the risks and to contribute for the sustainability. Complying with the SENDAI framework for disaster risk reduction, IHRR envisions to understand the risks and applications of interdisciplinary knowledge with science, engineering, technology, and innovations to contribute for risk reduction and bridging of academic research with professionals and policymakers for the sustainability. So our team consists of professionals with expertise and experiences in the field of disaster risk reduction in understanding the risks, conducting academic research and field level implementations in Nepal and across the globe. So far we have successfully accomplished a transdisciplinary project that is, as you can see on the screen as well, the landslide risk assessment on Sino-Nepal road corridors. Similarly, we have had quite a number of engagements during this COVID-19 response, from developing swab collection booths to medicine carrying robots. And we have also engaged with the Ministry of Health and Populations in developing a national platform for COVID-19. So this is how we have been working, and we have also utilizing the lockdown period during this COVID-19. We have collaborated with a number of local governments to bring out the frontier technology, that is UAV surveying of Hetauda sub-metropolitan city for the very first time. Besides, we are also advocating the recently promulgated DRRM Act 2017, and as you can also see, we have also published our voluntary commitment in the official website of United Nations Disaster Risk Reductions Office for Disaster Risk Reduction. Similarly, we have also been conducting a webinar series separately on disaster risk reduction and geoscience for sustainable development. So we are having our second session for today on geoscience for sustainable development. And okay, so with this, I would like to, without any further delay, I would like to move on to the today's sessions. And now I would like to share some house rules for this webinar. The audio and video of the participants will be switched off. For any queries, the participants can write up in the chat box or in the comment section of Facebook streaming live. And waiting rooms have been enabled. So I would like to request you to please write your name as you have mentioned in your registrations. Otherwise, the users won't be allowed to enter the room. And only the registered participants will be allowed to enter the webinar due to some security reasons. And the entire session of the webinar will be recorded and will be shared after the succession of the program. So without any further delay, I would like to move on to our session, and may I request Dr. Basantaraj Adhikari to proceed with his moderation. Thank you.
Thank you, Suraj. Am I audible?
Yes, sir, you are audible.
Thank you, Suraj, for wonderful introduction about Institute of Himalayan Risk Reduction, and pleased to know lots of activities that you guys are doing. So without further ado, I would like to introduce today's speaker. He is my good friend. We met long before, and you know, Dr. Alexander Webb, he has done his PhD, and he first field was conducted in Nepal, in the Himalaya in 2003. And then after that, he has authored more than 30 papers on mainly on East Asian tectonics, principally focusing on tectonic development of Himalaya. And then his principal insights from this region have centered on the evolutionary models of mountain building, and then the role of mental processes in determining these process, evolutionary processes. So he's not only that, his other interests also from deformation of salt glaciers to the early development of terrestrial planets, and his career has taken him from the PhD and brief postdoc at the University of California at Los Angeles, and to post on the Louisiana State University, the University of Leeds, and now is working as an associate professor at University of Tectonic funding supports from the Research Grant Council of Hong Kong. So he has lots of experiences on these issues and topics in the Himalayan region, and he has produced really, really good insights and good papers. Some of his papers tackles or explain long hanging discussion about this thrust development and where and how, the location and others. So I am always fascinated by his work and dedication in this field. So today he's going to present on how mantle dynamics guided the main phases of Himalayan crustal tectonics, and I'm pretty much sure that his presentation or his talk will be great importance for geology graduates and other professionals in this region. So I would like to welcome Dr. Alex Webb. Please proceed.
Thank you for that kind introduction. Hello, everybody. Namaste. And I heard a little Chinese in the chat room, so Dajia Hao. Let me share my screen here. Okay. Yes. There we go. Can you see it? No, everything's okay? Good. All right, I'll assume everybody can see the screen. So thank you to the Institute of Himalayan Risk Reduction and Executive Director Suraj Gautam for inviting me to join this webinar series, and to Dr. Basanta Adhikari for hosting today. I really appreciate it. So I'm going to talk about mostly about crustal tectonics, but from a different lens than we are used to thinking about it. As Basanta said, I have I've been working in the Himalaya for many years, so I have been working with so many people who have supplied me with so many important ideas, and these folks are really the people that have been working on these recent ideas about how the mantle interplay may affect crustal dynamics, but there's a whole heck of a lot of folks behind them, and I'm grateful to them all. So without too much further ado, let's get into it. Before we get started, I want to introduce this diagram because it's going to be very important in the talk. And it's a funny looking thing. So I want you to imagine, in order to understand what we're looking at, I want you to imagine that you are in Beijing, except that you are, let's say, 2,000 kilometers above Beijing, and you're looking back at the Himalaya. So we're at northeastern China and we're looking back at the Himalaya, and we can see through everything that is Asian crust down to the subducting Indian plate. And finally, it's 15 million years ago. And that's roughly the view that you're looking at here. You're looking at a model of the Indian subducting lithosphere coming down below Asia. And what you see here are two tears in the downgoing plate. So this would be the Western Himalaya, and this would be the Central Himalaya, and this would be the Eastern Himalaya. And you see a tear emanating from the Eastern Himalaya inwards, and a tear emanating from the Western Himalaya inwards. And throughout this talk, especially in the latter parts of this talk, we're going to explore whether we believe this image, whether we think this is viable, and if we do, what does it mean? What would it? How would these dynamics of a steep and tearing downgoing Indian slab impact the growth of the Himalayan orogenic wedge? So that's going to be our main focus today. Again, sort of as a warm-up slide. I'd like to also, sorry, one bunch of folks I didn't acknowledge yet. The Research Grants Council of Hong Kong are the folks that fund this research. So to start off, we can look at cross sections of the Himalaya that I'm sure we're all familiar with. Sorry, just adjusting my screen here. So the top one, given our audience today, mostly Nepal-based geologists, I'm assuming that you guys know most of these faults. So the main frontal thrust, the main boundary thrust. This one would be known mostly to you and not so much to the wider Himalayan community, the Mahabharat thrust, and then the main central thrust. And then back in the back, which is somehow blocked by this participant thing on my screen. Let me see if I can get rid of it. Yes, I finally did. Okay, the South Tibet detachment. Sorry for that. So we're looking at 4 different models for this cross section, and I'm sure we're familiar with many of them. But a larger point with all of them is that there's no real mantle involvement. The base of these cross sections is, in pretty much all cases, the main Himalayan sole thrust. So the main Himalayan décollement, or the sole thrust of the Himalaya, however you want to call it, the main frontal thrust at great depth is the bottom of these cross sections. So we're thinking of this system primarily in terms of its crustal components and treating the mantle component as a background converging component that allows it all to happen, but is in a relatively static or an interesting geometry. And I'm going to suggest that if we start thinking about what the mantle is doing and its dynamics through time, it's going to change how we think of the main phases of development through these cross sections. All right, so I want to talk first. We're going to go through a historical overview of Himalayan tectonic models before we go and look again at the mantle. But I just want to emphasize at the earliest stages of Himalayan tectonic models, we were thinking about the whole lithospheric section. So this is Emile Argonne's work in the Tectonics of Asia, showing India underthrusting beneath the Himalaya and Tibetan plateau. And this is pre-plate tectonics, but he is essentially showing the whole plate here. And when you get to Dewey and Bird, it's pretty similar. The whole plate is involved. But once we discovered the South Tibet fault, the South Tibet detachment system, whatever your preferred name is, then things got more complicated. So this is one of the discovery papers of the South Tibet fault, or the South Tibet detachment. So it runs along the length of the orogenic system, parallel to the main central thrust, thought to be active in roughly the same periods as this main central thrust. And so this is one of the discovery papers in the East Central Himalaya. And the models that we developed once we started thinking about the South Tibet fault, the South Tibet detachment system, started to really focus crustally almost entirely. So we started, the earliest models were these wedge extrusion models involving the greater Himalayan crystalline complex, or some people call it the high Himalayan crystallines, the crystalline core of the origin, extruding as a wedge between the South Tibet detachment and the main central thrust, bringing those high-grade rocks to the surface between 2 low-grade sequences. And this would be in the early to middle Miocene. And this model largely transitioned into the classical channel flow focused denudation model. So the basic kinematics were a little bit reconfigured. Folks started thinking about how with a thickened crust beneath Tibet and beneath the high Himalaya, that would become thicker and that would become hotter, and it would maybe potentially partially melt and greatly reduce in overall strength. And with the high gravitational potential of the Tibetan plateau atop these relatively weak rocks, they would be squeezed out towards the margins. So squeezed out towards the front of the Himalaya. And then as they transited towards the front of the Himalaya, with the onset of the South Asian monsoon, this would cause a erosional advection of crust from the depths of the middle or lower crust up towards the surface and extrude the high-grade rocks in this fashion. So again, the high-grade rocks are making it to the surface in the earlier middle Miocene. And then this is a model I've been associated with in which none of this extrusion is happening, and the South Tibet detachment is envisioned not as a normal fault, but rather as a back thrust surfacing as the great counter thrust. So a back thrust emanating off of the main central thrust when the main central thrust was effectively the Himalayan soul thrust, and surfacing as the great counter thrust. So how are we going to test these models? How did we test these models? Our primary approach is to look at a geometric element that's different between these models. So in these two, the high-grade rocks are getting to the surface in the early to middle Miocene, whereas in this model, they're still at depth, potentially mid-crustal depths in the early to middle Miocene. And a key feature is that in cross-section, as we view it here, we have a line representing the main central thrust and a line representing the South Tibet fault, and they intersect at a point. In nature, of course, these are two fault planes which intersect as a line. So we can search for that line in the Himalaya today, and if we can find it exposed, well, that's pretty good evidence that the greater Himalayan crystallines weren't eroded away at the surface 10, 15, 20 million years ago, but rather the frontal tip still being preserved now would indicate that they were placed at depth back at that time. So we looked for that line, and this is essentially our group's interpolation of where it ought to be. Oh, sorry, going the wrong way here. And these are the places we've studied to find it. So my PhD work was out here. We published papers on this in 2007, 11, 13. A paper in this area in 2016, papers out here in 2011 and 15. And this is largely interpolated from literature data. And in this area, we have a lot of good data, but we're waiting on a single data set, and then we'll publish something for Zanskar too. In general, we think we can see this geometric element in many places. So let me show you one of them that you're probably pretty familiar with. We're going to go to Galchi. So here is Galchi, and many of you have probably seen this view. So there's Galchi village. Here's the bridge. Back over there is the main highway from Kathmandu to Pokhara. And here we have the Trishuli River, and here's the Mahesh Kola going to join the Trishuli River. And so for those of you who've done field work or student work in this area, you know that this panel of rocks here and all through the Trishuli River area, when you find bedrock exposed, it's typically the main central thrust shear zone. And then in here we have slivers of gneisses, and eventually we get up into the Bimpeti group. So our group argues that these slivers of gneisses are essentially Shiopuri, which we equate to the greater Himalayan crystallines. But then if you get over to about here and a little bit further off to the left of the image, we think that you have the preserved South Tibet detachment. So again, the main central thrust here is steeply south dipping, and moving south is moving up section. So you're in lesser Himalaya, then through the main central thrust, then we think a small sliver of greater Himalayan crystallines, and we argue that a shear zone called the Galchi shear zone is in fact the southern continuation of the South Tibet detachment, coming very close to its merger with the main central thrust. So I can show you a little bit of data on that before we move on. So here's Kathmandu Basin, there's Galchi, here's the Trishuli River, here's the Mahesh Kola. So we can zoom in here, the Trishuli River again, and you have the main central thrust shear zone pretty thick, and along the Mahesh Kola is exposed a second shear zone with kinematics that are in the exact opposite direction of the main central thrust shearing. They're all torqued a little bit funny, but so is the main central thrust because of the non-cylindrical folding of the Kathmandu Klippa. But in essence, you have a lot of structures, and you can see it in quartz microfabrics, and you can see it just in the field, a lot of top to the north structures in these gneisses. So beautiful shear bands, and beautiful SC fabric and Sigma class, all indicating the same kind of shearing that we've seen elsewhere in the Himalaya along the South Tibet Fault. And so when we look along the northern margins of the Kathmandu Klippa, we have that Shiopuri gneiss backstop. The hills above Kathmandu to the north have the Shiopuri gneiss up there, and along the contact between the Shiopuri gneiss and the Bimpeti group, we see those same shearing features everywhere. And so we can track the thickness of the potential Shiopuri gneiss unit, and you can see it in a series of cross sections from 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, going along the northern margin of the Kathmandu Klippa, where it all seems to pinch out towards the main central thrust. So we envision this basic picture for the structural geometry here, where you have the South Tibet attachment nearly parallel to the main central thrust, but joining it to the south in that branch line. So let's keep. So this brings us back to that overall geometry of having the branch line still preserved locally in the range, marking that frontal tip of the high-grade rocks, and leads us to favor this particular model. And whilst we were doing this work in about 10 years ago, other groups were really focusing a lot on the internals of the greater Himalayan crystallines. And they were seeing a lot of 1, 2, or 3 thrust faults within the greater Himalayan crystalline complex, building this complex above the main central thrust, essentially as a thrust system that propagated from north to south, so forward propagating thrusting. And when we take forward propagating thrusting and we combine it with the overarching geometry that we think we can define with the South Tibet attachment at the top, we end up with something fairly classical, something that looks like a pretty standard duplex system with an active roof back thrust. So this was kind of our state of the art about 5 years ago, and you know, this was what we thought. Many people still argue in favor of the channel flow model, and I'm not really here to convince you either way today on those, except I would like you to have some sense of the plausibility of fitting in a duplex model, to see it as a reasonable possibility, because that's going to help later. So more to the fundamental point is that if we look at these models through time, we move away from the whole lithospheric scale and mantle scale to more of crustal scale models and even subunit models. And this is where we say the state of the art is. Other people are here. But again, the state of the art is not looking at lithospheric scale. It's looking at crustal scale. And the state of the art is also two-dimensional. And I'm going to suggest that that's a problem also. So let's start with the two-dimensionality being a problem. And the best place to start for that is actually that same fault, the South Tibet fault, or the South Tibet detachment system, because the timing doesn't work. The timing for the South Tibet fault or South Tibet detachment system is not something that lends itself to a two-dimensional situation, because it stops motion in the Western Himalaya far earlier than it does in the East Central Himalaya. And it appears to progressively stop moving along strike. So let me show you some data to back that up. And I have to admit, it's quite messy looking. Once you understand the data sets, I think it will make more sense. But it's going to look like a Rorschach at first. So here we are. Here's what the data looks like. Now, let's step into this plot slowly. It's just a Cartesian plot. So in some senses, it's pretty simple. This is longitude. So this is the Western Himalaya, this is the Central Himalaya, and this is the Eastern Himalaya. So we're moving along strike, and this is time moving forwards. And the data plotted here are ages relevant to South Tibet fault motion timing, okay? So the classical ways of dating the South Tibet fault is you date deformed leucogranites, or you date undeformed leucogranites, or you look at argon muscovite ages. So argon muscovite ages should be post-fault motion, because they should be cooling after the fault was active, because the fault seems to be active at higher temperatures than any plausible closure temperature for argon mica, argon muscovite. However, there is the challenge that sometimes argon muscovite systems, particularly in the Himalaya, get excess argon in there. So the ages get too old. So it may give you a falsely old age. So these argon ages are suggestive, but individually they're not going to be perfect. Okay. The same thing is true for post-fault motion ages of undeformed leucogranites. And the reason for this is that the undeformed leucogranites, in my opinion, not everybody's, but in my view, there is not a single undeformed leucogranite that is proven to cross the entire South Tibet fault system. There are a group or two that disagree with me, but you know, we have a disagreement. If the undeformed leucogranite doesn't cross the entire fault system, then it may be showing you that some of the fault has ceased motion at this time, but it doesn't show you that the part that it doesn't cross has ceased motion. So again, these ages are pretty strongly suggestive that the fault has stopped motion, but they're not fully encompassing. There can be a little bit of fuzz on that. The pre or syn fault motion ages come from deformed leucogranites. So you date zircons or monazites in a deformed leucogranite. That tends to be more robust. There aren't really a lot of ways to get around those ages. If you have a leucogranite that crystallized and then was deformed, it's either crystallized before or during the fault motion, and that's a pretty good indicator that the fault was active at or after the ages shown in green. So we can really trace the youngest margin of the ages shown in green, and I delete a couple of outliers, but everything else can be interpolated in this gray band as showing you that the South Tibet detachment ceases motion earlier in the Western Himalaya and then progressively younger and younger until like the classic Edwards and Harrison data showing that it's still active at like 12.5, 13 MA in Bhutan. And then there's a suggestion in the data that it may be active, it may cease motion much earlier in the far eastern Himalaya, but the data is not particularly strong in that area. It's hard to say that this is valid. But this trend is pretty strongly robust. So what this apparent Rorschach of data is showing us, once we especially focus on the pre-syn fault motion ages, is that the South Tibet detachment is stopping motion far earlier in the Western Himalaya, but continuing motion progressively younger and younger and younger until it finally stops in the last place at about 90 east, about the longitude of Shigatse or Sikkim, something like that. This is weird. This doesn't fit with these models. These models show the South Tibet detachment and main central thrust as basically the same along the entire origin because they're 2D slices. Whereas this is showing you, you've got a plus 10 million year age swing in when one of those major faults stopped motion. This is not going to lend itself to a two-dimensional model. So, you know, whether you prefer channel flow or you prefer my model, it doesn't matter. They're all needing improvement. And we need to be thinking in 3 dimensions. So that's really a major takeaway of this talk. If you want to fall asleep for the rest of it, but if you recall that the two-dimensional model isn't really going to supply you with a very robust understanding of Himalayan tectonic development, cheers to that. That said, let me try and persuade you anyways. So we're back to our model looking at the Himalaya, but we're able to see through the accreted Himalayan material and the Asian lithosphere, and we're looking from atop Beijing back at the Himalayan front. Here's the ridge crest of the range, and this is the downgoing Indian plate, and we're arguing that it tears at both ends and propagates into a final breakoff in the middle. So this is just a snapshot of it at about 15 million years. And the important factor to think about is that, of course, this is mantle processes, but what are those mantle processes? What is a slab rolling back and then breaking off going to do to the overriding orogenic wedge? How is it going to mess with it? Could it mess with it? It probably will because it can control the sole thrust. It'll affect the sole thrust just by the distribution of weight at depth. So before we really get deep into that, I want to talk a little bit about mantle dynamics because there's a lot of ways to talk about mantle dynamics, and I'm going to go very simple in this talk, and we can stay very simple in this talk. We don't really need to think about the full richness. We can think of it in the classic Cox and Hart sense of all of the forces acting on a plate. We can think of it in terms of the convection necessary to continue to maintain the convergence of India and Asia after these slab breakoff events. We can think of mantle dynamics in terms of dynamic topography, how the rising of hot mantle and sinking of cold mantle may impose stresses on the lithosphere that will raise up or diminish the topography in ways that we wouldn't otherwise expect. But for the purposes of this talk, what we see here at the right is good enough. Recall that the slab is very heavy, and if you distribute it differently, if you change where it is through time underneath the orogenic system, that weight will impact what's happening above it. And I'll show you some ways of how. So that's really our fundamental, that's the only way it's not the only thing relevant, but we can break it down to just focusing on that and go through the story just via that particular way of thinking of the mantle dynamics. So let's look at what the slab has been doing through time according to other folks' work. This is not my work. We're going to focus mostly on Anne Repluma's look at seismic tomography, and we'll look at Pete DeSalle and co-authors and their look at volcanism across southern Tibet and what these things can tell us about the activity of the slab through time. So Anne Repluma's seismic tomography first. We're looking at snapshots today through the top half of the mantle and the lithosphere from the Western Himalaya here at 75 East to the Central Himalaya here at 84 East. So a bunch of slices, and what you can see here is the cold Indian cratonic lithosphere, and you can see the 660 discontinuity in the mantle, and you can see cold anomalies at depth. Cold anomalies in mantle seismic tomographic images are commonly interpreted as potentially being delaminated portions of the lithosphere or broken off slabs, some portion of lithosphere that's falling down and is cold relative to the rest of the mantle. So in this case, there's two anomalies that Repluma and colleagues are focusing on. There's what they call the Tethian anomaly and what they call the Indian anomaly. And it might help to just look at Pete DeSalle and co-authors, their model, to show what those are in a sort of more standard tectonic sense. So here we have 60 MA to 20 to 15 MA, and we're going to show two breakoff events in this model. One breakoff event of oceanic lithosphere, and then a second breakoff event of continental lithosphere. And those two breakoff events are essentially what Anne Repluma has previously interpreted as this Tethian anomaly and this Indian anomaly. So DeSalle and co-authors are building off of this work, but it's still easier to see it here. So let's start here. So here we have India and the Tethian oceanic lithosphere approaching Asia. Here's initial collision, at which point the oceanic slab detaches and falls into the mantle. Following this, DeSalle and co-authors argue that India underthrusts Asia and then rolls back. Now, another way of thinking of this is, we'll talk about it as rollback for the rest of the talk, but it's more plausible that the lithosphere actually gets fixed in the mantle, but the orogenic system is moving to the north over it, such that by being fixed, it is rollback relative to the orogenic system. And then, so with this rollback, eventually this slab of Indian continental lithosphere detaches and sinks into the mantle following the Tethian anomaly from earlier. So these two anomalies are where DeSalle and colleagues are getting that particular breakoff story from this work from Anne Repluma. Now, let's look back at Anne's work because there's a signal distinction that allows us to reconstruct a better picture of what the mantle may have been doing through time, and what the mantle lithosphere may have been doing through time. So the Tethian anomaly is down there. Let's focus in on the Indian anomaly. So again, this is the Western Himalaya, and progressively we're moving towards the Central Himalaya. In the Western Himalaya, this Indian anomaly is entirely below the 660 discontinuity. So this is 660 kilometers below the surface, and the Indian anomaly is entirely below that line. But as we move further and further towards the Eastern Himalaya, to the Central Himalaya, that Indian anomaly is progressively shallower and shallower, such that here it's halfway above the 660 discontinuity. This suggests that it's had a longer time to fall in the West, so it fell all the way below the 660 discontinuity, but it hasn't had as much time to fall in the Central Himalaya, so it's still halfway above the 660 discontinuity there. And this led Repluma et al. To make a model that is what our other model that I showed you earlier, the view from Beijing, is based on, where they said that they interpreted that in the Western Himalaya, a tear initiated at about 25 million years ago, and that tear propagated towards the Central Himalaya by about 10 MA. So that tearing of the slab is how they interpret this progressive shallowing of the Indian anomaly, that the tear started earlier in the West and far later in the Central Himalaya. Okay, so let's move forward. So that again is sort of what we're showing here. You can see that Anne Ripley-Ma's picture here is very similar to our picture here, where we show this tear propagating from the Western Himalaya towards the Central Himalaya. And I also want to point out another couple things about what you can get from volcanic data. So classically there's some atacitic and high potassium volcanic rocks in southern Tibet. And they do a couple of things that are a little bit surprising. So first of all, according to this Decel model, they show this underthrusting of the Indian continent, and they interpret that volcanism moves northwards with that underthrusting. And then with the rollback, they interpret that volcanism moves southwards. So this is their compilation of data to back up that interpretation. I've put the interpretation before the data, but of course they did the opposite. Where they're showing you the distance north from the Indus-Yellow Suture. So this is the Indus-Yellow Suture, and this is progressively further north into Tibet. And this is time, and showing volcanic data. So the volcanism is sort of spread around, and then it all migrates to the north, and then it all migrates back to the south. And they interpret this, again, to show you underthrusting followed by rollback. So that's one way you can use the volcanic data. Another way that the volcanic data has been previously used is to suggest this tear, so independent of Ripley-Ma's work, and then also to suggest this tear, a tear from the far eastern end of the Himalaya towards the east central Himalaya. So if you look at the high potassic and atacitic volcanism, and you look again from the western Himalaya to the central Himalaya to the eastern Himalaya, and again through time, you see two trends. There's a trend like this that previous workers have identified, and a trend like this that previous workers have identified, both of which are interpreted to show the propagation of a tear, allowing mantle to slip through and heat the base of Tibet and create this volcanism. So I'd point out that this picture of a propagation through time along the strike of the Himalaya, it's relatively similar what we see in the magmatic ages to what we interpolated for the cessation of timing on the South Tibet detachment. So if the magmatic ages are indeed showing us orogenic records, orogenic wedge records, and the South Tibet detachment is showing us what the orogenic wedge is, sorry, I think I mixed that up. The South Tibet detachment is showing us orogenic wedge records. The magmatic ages are presumably showing us slab records. It's suggesting that the two are correlated. And there's ways of looking at this also in the Fourland Basin record of thermochronological data. And I'll just flash some of that here so that if we wish to come back to it later, if there's any questions about how the Fourland would show this, we can come back to this slide. But we can simply move on to the model for now. So I've talked about an argument that these slab dynamics are going to affect what's happening in the orogenic wedge. And so this model is a representation of what's going on in the orogenic wedge that I'm going to use to illustrate that. And I know it looks like a mess and it's way too tiny for us to see right now. So first we're going to talk about the guiding principles that allow us to think through this model. And then I will take you through it stage by stage and you know, you can see what you think of it. So guiding principle number one, we've already talked about, which is that the slab itself is quite heavy. And thus its distribution is going to impact the dynamics above it. So for instance, if we look at this period here, there's a caveat I want to point out. We're going to treat the mantle as essentially inviscid here. We don't have to, and it wouldn't matter with things that much, and I'll explain to you what the difference will be in just a second. But if we treat the mantle as inviscid, then that means it can't really transmit stresses very much. So if we have the weight attached through the mantle lithosphere, sorry, we are treating the asthenospheric mantle as inviscid, not the mantle lithosphere. So if the slab is attached, then it's pulling down on the system. If the slab is detached, if it's just broken off, and the asthenosphere mantle can flow easily and is very low viscosity, then now it's not pulling down on the system anymore, and so the system can pop up. So whether the slab is pulling down and steepening the sole thrust and steepening the whole system, or whether the slab is broken off and thus the whole system can bounce back up, really impacts the basal thrust of the Himalaya. And the basal thrust geometry will impact everything else. So let me show you the other way of thinking about this. Let's say that, and again, for the model, it's going to change the timing relationship to the slab, but it's not going to change anything in the crust. So we're cool with either way of thinking about it. This waiting room thing keeps popping up on me, which means I can't see this portion of my slide very easily. So this is what I need to show you now. So we'll see how it goes. Anyways, if the slab is attached or simply in this position, even if it's broken off, that's a huge weight that pulls down on the topography directly above it and helps allow this topography in the subducting plate to stay pretty high. But if the slab detaches but also moves out of the way, so the orogenic system moves to the north relative to the slab, or the slab moves to the south relative to the orogenic system, which one of those two is happening, then with the slab moving from here to here, now that weight with a viscous mantle is pulling down on everything above it. So it's pulling down the foreland basin, but it's not here anymore. So this area pops up. So the Himalaya pops up. So essentially you're going to have the same dynamics in terms of uplift and topography and the sole thrust, whether it's viscid or not. But this model is going to treat it as inviscid just for simplicity's sake. All right. So again, slab attached, heavy. Let's move on. The other thing that is going to be critical is thinking about critical taper. Thinking about critical taper. The critical taper model is really a first order way to think about how mountains are built from a crustal perspective. And it's essentially thinking of a bulldozer pushing a hill of sand. And this hill of sand are your mountains. So in the case of Tibet and the Himalaya, this Tibet would be sort of your backstop, and this would be the Himalaya. And there are a few key parameters in this simplified way of thinking about mountain building. So there's the angle from horizontal down to the basal décollement, and there's the angle from the horizontal up to the slope of the mountains, going up from the plains of India up to the plateau of Tibet. So that's slope. So those two angles put together is your critical taper. And there's the friction along the base and a few other parameters, strength of the materials. Essentially, if you mess with one parameter, the whole system adjusts. Because if it's going to be approximated by essentially sand piling up, everything can fail. Anything in there can fail. It can adjust instantly to any change in any parameter. Again, this is just first order. It works at first order. That's all we really need to think about it at. So that means if you mess with the basal décollement, then everything else should change. So let's look at this just in a practical sense. We know that mountains aren't fully failing everywhere, always internally, and that major structures tend to accomplish the failure. But nonetheless, if you count up the major structures and the overall shape embedded in them, there are bumps along the way, but they tend to have something similar to a taper angle at the top and a taper angle at the bottom, such that this loose approximation has first order validity. And then if we flip these around, because I need to use this diagram, if we think about what happens when we mess with the taper, when something changes, when a parameter changes, now it's time to start thinking about how can a real system adjust? So let's say we steepen it. So if we steepen the sole thrust, then everything moves down, and so everything needs to thicken to get back to some sort of an equilibrium taper. And so the means of thickening could be taking material at depth from the downgoing plate and scraping up more of it. So duplexing or underplating to the orogenic wedge, as we see here. It could be internal back thrusting. What if we need to do the opposite? What if the sole thrust angle shallows? Well, then the orogenic wedge is going to want to collapse, and it can do that by collapsing with normal faults in the hinterland. It can do that by growing outwards rapidly and thus decreasing the overall taper angle. The essential point is that the orogenic wedge will respond to changes in those variables. And the slab, by virtue of its weight, can change the basal angle. And so it can change the behavior of the orogenic wedge. And so what we're going to do in this model is we're going to track through time and see how the slab dynamics may have changed the basal taper and thus the dynamics of the orogenic wedge. Okay, so let's start for 30 to 25 million years ago. And at this point, we argue that everything's fairly uniform along the length of the Himalaya. So we only show you 2 cross sections, one at each time. So this is following the Decel model, in which we have underthrusting of the Indian crust and mantle lithosphere far below Asia, and that's at 30 MA, and then it rolls back such that the weight of the Indian mantle lithosphere is now concentrated below the northern Himalaya. And so the sole thrust steepens because we've concentrated that weight, which is going to lead directly to orogenic thickening. So we can zoom in on this area and think about that. If we've got to orogenically thicken in the hinterland portions of the Himalaya, a good way to do that is to initiate a back thrust and to start duplexing. And so we see this back thrust as the South Tibet detachment initiated. And there's a lot of good reasons to think that the South Tibet detachment did initiate around 25 MA, a fair amount of geochronological data. And there are some arguments from the folks that have been working on the internals of the greater Himalayan crystallines that this is about the time when they start having thrusts building up that sequence. So that could be these duplex sheets. Okay. Now at 25 MA is when things are going to get different from the Reploumat model, because that's when she says, and that's when our reconstruction suggests that the tearing initiates in the downgoing slab, and it initiates at the western and eastern ends of the Himalaya. So now we have to look at multiple cross sections because different things will be happening at different portions of the Himalaya. So again, if the tearing is starting in the far west and in the far east and propagating inwards, then from 25 MA, everything's pretty much the same. The tearing is just going to start in the west and east. But by 20 MA, say the Sutlej area of the Himalaya, Shimla area, is going to just be experiencing the tearing. It's just going to have torn off. And in the east central Himalaya, at about 90 degrees east, it's still firmly attached. So with this tearing, now we're not pulling down on the sole thrust anymore. It all can bounce up. All of this duplexing can shut off. The back thrust of the South Tibet detachment can stop motion. But in the east central Himalaya, we're still pulling down. So we're still steepening the sole thrust. So we're still duplexing. So we're still back thrusting. And so with this lateral migration of slab detachment, we're having different things happening in different sectors of the Himalaya. And this is, again, driven by weight. And it's a nice illustration of why we could have this change in timing of when the South Tibet detachment stopped motion. If you break off this slab, so you can see the Western Himalaya 77 east. So about here, it should have stopped motion somewhere at 2220 MA. And that's what the data shows happened to the South Tibet detachment. How can we explain it stopping motion then when it's still very active here and it's not going to stop motion there for another 10 million years? Well, maybe the slab broke off and that could allow it, whereas the slab's still attached here and so it's still humming along. So it's a potential explanation for this data. Okay, so now we just bring it home. We have that propagation of slab detachment migrating along the length of the Himalaya, such that at 15 MA at 90 east, it's still attached, but it's one of the last places attached, and to each side it's torn off. So there's a lot of weight here because it's supporting some of the side weight too. And so you're really pulling down and building a very thick greater Himalayan crystallines. It's interesting to note the greater Himalayan crystallines in, say, Bhutan is like 20 kilometers thick. In the Sutlej area, it's maybe 6-7 kilometers thick. So there's very great thickness variations in this unit along strike. That could be due to exposure level, but it doesn't seem necessarily like that's the only possibility. So, okay, so we focus on the Western Himalaya, 20, 15, 10. Everything has already broken off at this point. So we've resumed underthrusting, and you start to build the Lesser Himalayan duplex because with the resumed underthrusting, there's no need to duplex at depth, but you can still grow the wedge at the front. Whereas in the East Central Himalaya, this slab remains attached, pulling down, creating this thick duplex with the back thrust. And only with the final detachment does that stop at something like 12 MA. And we envision that there may be, because of this final detachment being a relatively dramatic event, because there's no side support anymore, it's the final break off where everything is going to bounce up, maybe that would lead to some out of sequence faulting and potentially some wedge extrusion in that area. We know that from Everest to Sikkim to Bhutan, there is actually a late normal fault cutting across the thick ductile fabrics of the South Tibet detachment system, and perhaps reusing them in some places like Everest. But say Northern Sikkim with Don Kellett's work, it's definitely cutting across those fabrics. And we interpret that as being this kind of a structure. And we know that there's out of sequence faulting also in the greater Himalayan crystallines from, say, Kyle Larson's work and Georgi Grujic's work. So we interpret those out of sequence or late faults in this context of a late wedge extrusion associated with the final slab detachment. And we note that that helps explain why it's so localized. It's only in the East Central Himalaya and nearby zones. It doesn't extend to the west of Everest. Okay. So now I want to focus, that goes through the crustal dynamics. And I've made an argument for how and why the mantle dynamics, which we just simply focused on as if the only thing that matters is the weight of the slab, it's an approximation, could impact the crustal tectonics. Now I want to also point out that it's going to affect all of the uplift, it'll affect the topography. So what we show here is the ridge line of the Himalaya. Again, the Himalaya is invisible, but we can show the ridge line. And where the slab is broken off, that's releasing a lot of weight, so the sole thrust bounces up, but so does the ridge. So you're growing topography here. Where the slab is still attached, it's pulling down, the topography is subdued. So you should be zippering in with high topography from the western end and from the eastern end to the east central Himalaya from about 25 to 12 MA. That's a prediction of this model. So something to point out is that the South Asian monsoon is known to be highly dependent on topography, on orography. So if the orography increases, which this plot is showing here from a model in 2014, as the orography increases, so too does the strength of the monsoon in a fairly linear relationship. And so the model is predicting you get a progressive building of high mountains from 25 to about 12 MA, and that these higher mountains should lead to a stronger monsoon. And if we look at monsoon records, we do not have great monsoon records in the Miocene. So full stop, it's hard to see. But to the extent that we do have those records, they are consistent with the strengthening of the monsoon through this period. So this is Peter Cliff's classic work, where here using the Pearl River Delta as a proxy for the monsoon without impacts of tectonics. The Pearl River Delta is thought to be in a sustained shape through that period, so that you're looking at what is hoped to be a pure monsoon signal. We think that if that's true, then this chemical weathering index, which is roughly a proxy for the strength of the monsoon, shows that from 24, 23 MA, you have a progressive strengthening of the monsoon with the exception of the global mid-Miocene climatic optimum until about 12 MA. So this growth in monsoon strength is consistent with the predicted growth in orography in this model. Now, I would hesitate to say that it's a really great test of this model in the sense that a lot of Himalayan tectonic models predict that through the early and middle Miocene, you should have a growth of topography, but it is consistent with this model. So I think we can mostly leave it here and take questions, but just to wrap up, we went through a lot of Himalayan tectonic models. And we spoke about how they started at lithospheric scale, and then with the acknowledgement of the South Tibet detachment as a major feature of the system, we started really looking crustally. And innovatively, we looked at the crustal dynamics as they were relating to precipitation and to climatic systems. But we didn't spend a lot of time thinking about the mantle dynamics. And I've argued that they can explain some things that we haven't explained previously. Including South Asian monsoon intensification. And also, if you're thinking about potentially enhancing the South Asian monsoon and raising up the mountains higher, then you're changing ecosystems enough to start thinking that you might be impacting biodiversification. So there may be some further tests going into biology. And I guess the two take-home messages I would say is that irrespective of the details here, I hope that I have persuaded you that million-year timescale Himalayan tectonic models improve if we think about them in 3 dimensions, and they improve if we think about mantle dynamics, because mantle dynamics is a huge player. The main strength of the lithosphere is through the upper mantle. Mantle dynamics impose huge tractions on the lithosphere. It would be awfully surprising if Himalayan crustal tectonics went through its evolution with the mantle as essentially a static boundary condition, especially when we know the mantle is so dynamic. It's redistributing so much weight, it's almost certainly affecting those dynamics. So whether this particular model is going to prove viable or fail tests in the near future, I can't be certain. But it does seem to me fairly persuasive that we need to be thinking in 3D, and it's time to start paying a little bit more attention to the mantle dynamics. So with that, I'll thank you very much. Thank you again to the Institute of Himalayan Risk Reduction. And I hope you may have some questions. Thank you. Namaste.
Thank you, Alex, for your comprehensive presentation, because this is the subject, where we have lots of theories and lots of controversies, lots of studies, starting from Eastern syntaxis to Western syntaxis, and from cross to mantle. And there are lots of models like what you rightly mentioned about this channel flow method. And there are lots of, maybe people already know about that. One journal, which is the Journal of Geo-Science, is really dedicated on these Himalayan models and others. So, and yeah, it's a long hanging discussion always. And I'm pretty much sure that we have done pretty good job in terms of Himalayan evolution and their relationship with the tectonic upliftment and others. I'm pretty much sure that there will be some questions in the chat box, but let me start from myself. Alex, are you there?
I can hear you, yes, I'm here.
Okay, good. So, I will start from Nepal, because when you publish a paper on this STDS in Gulchi section, and it was created really, really discussion on how, you have interpreted this STDS near to the MCT in Gulchi area, which created lots of discussion and argument, NT and pro. And, when you are talking about a thrust and fault system in the Himalayas, and there are lots of, techniques to really identify and differentiate. Some of them are, maybe you look on mineralogy, you look on dating, you look on structural relationship, and, in the same area, just, eastern part in Maleku, people are again talking about main thrust, Mahabharat thrust, and, some people talking about Ramgarh thrust over there. And so it's a complex phenomenon in central Himalaya. And then now we are talking about this mantle tectonics and crustal tectonics. So, how you take this discussion, you have presented very well, but particularly in the central Nepal, how you explain to our audience more clearly about how you believe, or, when you explain about the tectonic wedges, then this, higher Himalayan region, higher Himalayan crystallines comes up, and then the South Tibetan disatonal system goes down, and ultimately, it created a sequence of normal faults. So how you relate these, things in central Nepal? Can you give a little bit explanation on that?
Yes. Some of your question was almost philosophical, and I'm going to use that because I do think it's almost a philosophical issue at this point. And so I am a structural geologist, and we have a particular philosophy. We think that in order to solve a geological question, you essentially have to answer 3 questions in succession. You have to say to yourself, what the heck am I looking at? What is it? What is the geometry of this tectonic system? How did it get into that shape? So what are the kinematics that gave us this geometry? And if you can answer those 2 questions, then you have the opportunity to say, okay, I know the motion, I know the kinematics, I know how it happened. Why did that happen? And there's a flip side to this, which is that in academia, we have people that are really good at geometry, we have people that are really good at kinematics, and we have people that are really good at mechanics. And each of those groups are working independently and together. And sometimes advances on one front, you know, conflict with advances on others. And for me personally, I think you need this foundation of geometry in order to say anything mechanically. And so when you have this elegant geometrical predictive difference between the channel flow models and the wedge extrusion models versus the tectonic wedging model, which is the preservation of the frontal tip of the greater Himalayan crystallines, the preservation of the South Tibet detachment and main central thrust intersection at depth, that's a powerful geometric prediction that can that you can go test in the field and see whether that actually is there or not. And so, you know, it's not terribly relevant to the mantle dynamics aspect, because the mantle dynamics aspect should honestly, even if you believe channel flow, even if that, or I don't mean to say believe, even if that's your preferred hypothesis, it still should be fairly impacted by this, by what the slab is doing in depth. But nonetheless, we didn't start there. Nobody started there, right? I mean, we published these models in 2015 after publishing for nearly a decade on Himalayan tectonics. Everything we ever showed is crustal scale. Everybody's trying to figure out this crustal scale pattern. And for us, that simple geometry is a powerful way of testing the models, and we really went at it. It's still a little bit debated. We published our second paper for Galchi, for instance, in 2015, and at about the same time, another group published a paper. We used their figure early in this talk, the Canal et al. 2015, which has a different interpretation. And I really think that the geometries you can figure out by reading all of these papers gives you an answer. And we will also bring out some more data pretty soon. We've got, I showed you some quartz crystallographic axis data. We now have that at 20-meter spacing across the whole system, just to really nail down what's moving north, what's moving south. And I can tell you that it shows essentially the same pattern I showed you today. So we have this. You'll have any particular group saying, yeah, we definitely see it our way, or we definitely see it our way, but we're all talking crustal. And something that had bugged me since my graduate student days is that I'm focusing on the South Tibet fault, and I can read papers from all along the arc to help me think about it and to try and see what the commonalities are. And the structural commonalities along strike are profound. For instance, you always have the kyanite in isograd right way up within that shear zone. It's never not there. Things like that. There are some things that are just always associated with the fault, but something that was never associated with the fault properly was timing. It's always fuzzy. People say that there's a certain range of, say, 23 to 12 for the MCT, 23 to 12, or maybe 23 to 16 for the STD. But if they point at any one section, maybe there's not quite enough data to really lock it down too hard. If they point at a lot of sections, they don't quite agree all the time. And anybody who's worked in both Zanskar and the Central Himalaya knows that there's a difference. We just don't think about it that actively. We don't put it at the front of our brain. And I finally had the opportunity to have to force it to the front of my brain, and I had no explanation for it. And I happened to have read Anne's paper, the Repluma paper, and I just started guessing. So you know, something's got to explain it. Maybe it is purely crustal, but I think that this is an awfully nice correlation between the timing of what other folks have interpreted as a lateral migration and slab tearing and what we see in the lateral migration of South Tibet detachment cessation. And if that correlation is causality, a whole lot of things come with it. So that's sort of how we get there.
Yeah, thanks, Alex. So maybe you can just see the question in chat box. I will take some of the question from there. Okay. So Krishna Kumal is asking, thank you for a good presentation. I have a question regarding the record of monsoon data. So what are the criteria or indicators are used to determine the monsoon during the formation of Himalaya?
Yeah, okay. So I am by no means an expert in this. This is where I definitely defer to my colleague, Peter Clift. But they use a variety of indices. And my understanding is that Peter and his colleagues use a variety of indices largely gotten from boreholes in the fans of chemical weathering. So I don't remember what all of these indexes are, but they're I think potassium versus aluminum, or another one is CIA, I think is the acronym. So we can look it up in that Cliff paper, but essentially you're looking at different means of trying to evaluate how much chemical weathering there was as a proxy for monsoon intensity, and other things. So trying to reconstruct sediment volumes might give you an indication of the monsoon if you think that's directly controlling the erosive budget. If you don't, then you don't. Essentially looking at multiple lines of evidence of those types helps to build a picture, but it is a very fuzzy picture still, particularly for the early and middle Miocene. A major challenge in building such a picture is, so imagine you're looking at the Bengal fan. The Bengal fan is largely sourced from the Yarling Brahmaputra. The Yarling Brahmaputra through time is performing all kinds of river capture events. So you don't have a stable source for which to compare the changes in these chemical records you're using to say are chemical weathering, because it's constantly switching the dimensions of the drainage basin. So this is why the Pearl River was used by Clift et al. In 2008, because the Pearl River is thought to have a stable drainage basin through the key period of the early to middle Miocene. Again, it's tough. If you manage to figure out a way to effectively reconstruct the monsoon through the early and middle Miocene in a way that most people are persuaded this is viable and robust, that's a Science or Nature paper. It's just it would be a huge breakthrough, but it's been a real challenge.
Yeah, thanks, Alex. Yeah, it's always interesting to see how this monsoon was responsible during the Himalayan evolution and to form to cast these topographies. And when you talk about the Asian monsoon during the deposition of these foreland basins and others from Western Shivalics to Eastern Shivalics is quite different. Yeah, thanks for the explanation. So there's another question from Akshay Outkasi. So asking, as per your dynamic model, Western and Central Himalayan region faced slab detachment from 24 to 12 MA. As you said, in Eastern, there is a lack of data, but can you project the possibility of event in the Eastern Himalayan region? What's your hunch in the fate of slab dynamics and related mountain heights?
Oh yeah, this is a great question. The best that I can do with this is to assume that the simplest first order assumption could be that since we see a migration in the volcanism in southern Tibet, in the high potassium and atacitic volcanism from the eastern syntaxis to about the longitude of Shigatse, to about 90 east, and we see a similar migration from the western syntaxis to that same longitude, both of those may indicate, or are interpreted to indicate, slab detachment propagation, right? Slab tear propagation. So if we believe it for the West, we may as well argue that the same thing can happen from the eastern syntaxis to the east center, and that is what we do for our first order model. So we guess that the same thing is happening, even though we don't have the data resolution. And it would be an easy proposal to say, let's go get that data resolution. But as you know, the politics of that is you're never going to get really close to the India-China border in that region of the world, and you need to be close to the India-China border in that region of the world to do the appropriate work. So, so we can start with that guess. And also, I guess, if you can reconstruct things other than the South Tibet fault effectively, then that can help. I would say that the seismic tomography in that area is more complicated than from the Western Himalaya to the central Himalaya, so it is very difficult to use seismic tomography to be very certain that the same thing has happened. And that could be a test that the model fails, or it could be a result of later dynamics than the model period, making a more complicated picture. And I'm not really certain. We wish to investigate this. We've submitted funding to investigate that particular question, but we haven't been funded yet. So we'll see how it goes. Thank you for your question.
Thanks, Alex. So there's another question from Ajay Rautela asking, is mantle composition is same throughout the Earth, and how mantle composition and density affect the plate tectonics, especially in the Himalayas? So more theoretical question.
I have been hanging out with geodynamicists increasingly, and they have answers to these questions. I am not a geodynamicist. I can tell you sort of what I vaguely recall, which is so like a 2-order dimensionality to the mantle. This beams concept that there are potentially, there's definitely some compositional heterogeneity in the mantle, which can turn around and potentially create different strengths in the mantle, and thus potentially focusing mantle convection and having some preserved ancient portions of the mantle and recycling more recent portions of the mantle that might make the second order pattern stable. There are groups that I very much respect that think that you absolutely need mantle to push in order to have continued Himalayan convergence. The only other option that I am aware of is that the continued slab connection in, say, Sumatra and the other subduction zones of the Indian plate are still allowing India-Asia convergence to continue. But you know, since we don't have, since for 2 periods in the reconstruction of the origin, we lost our slab. Without something else pulling, you would have expected dramatic slowdowns, and you have some slowdowns, but really dramatic slowdowns in the convergence. So this does not perfectly answer your question by any means, but hopefully it gives you some sort of a window on the things people are talking about. And if you like, I can recommend some papers to check out.
Yeah, thank you. I can imagine that it's a little bit out of your scope from your expertise. Yep. So questions are coming in between. I think we'll stop taking questions after 5 minutes. So if you have any questions, please write down there. We'll take, and then we'll close our questions there. In the meantime, so there are 2 questions from Babu Sharma. The first one, the comparison between argon-argon muscovite edges versus the zircon-fissure track along in the slide, the first. And the second one is the slab dynamics different in central Himalaya that in the east and west?
All right, well, I think we're gonna have to go back through the talk for this. So I think that means we'll take the, I think we'll end up taking the second question first. So maybe we'll look at it here. So for the slab being different in the central Himalaya versus the east and west, I like to kind of focus on the timing of the South Tibet attachment. If that is a viable proxy, and if the volcanism in South Tibet and its east-west migration is a viable proxy for when and where the final breakoff occurs, then I would point out that the central Himalaya here is not where the final breakoff occurs, it's more here. It's 90 east, which is pretty far to the east in the Himalaya in this model, right? So I'm just talking within my model universe. The slab dynamics in the central and western Himalaya is pretty similar throughout this period, except that it's time transgressive, right? What happens in the west is the same thing that happens in the center, but it happens earlier in the west and later in the center before a final breakoff in the east central. And what's going on in the east is the same thing propagating inwards, just more slowly. So the same thing in reverse. So that east central area is going to have the dramatic final snap off. But otherwise things should be kind of similar. If you're curious, I can later talk about arc curvature. The Himalayan arc is actually asymmetrically curved, and that might reflect the difference in propagation speed of this tear. So anyways, I hope that answers your question at first order. For the second question, now let's go back to the fission track stuff. Okay, this slide. So this is looking at, I believe this is what you're asking about. Yeah, in the slide you say.
So, yeah, please, can you share the slide? Can you share the screen?
You see, oh, am I not sharing anymore?
Yeah, please share.
I'm sorry, I thought I was still sharing. All right, I'm sorry, I should have been sharing. I was talking about this slide last time, and apparently I wasn't sharing it. I'm sorry about that. All right, so now we are sharing?
Yeah.
You can see it? Okay, I'm sorry about that for the last one. Good, so you're asking about the distinction between the argon muscovite and the zircon fission track. The major distinction is argon muscovite. So in all of these systems, we're looking at compiled cooling ages in a single sediment sample. So take any one of these curves, all of them are going to end in a block somewhere. So find, the end of this green curve ends in a block. All of them are colored by longitude. So red ones are in the Western Himalaya, in the Siwaliks of the Western Himalaya. And blue ones are in the Eastern Himalaya and the Siwaliks of the Eastern Himalaya. And you can see how the colors grade along strike. Okay. So these are all representing samples of sediment from the Siwaliks that were then taken, and the materials were separated out. The muscovites were separated out and the zircons were separated out to collect for, say, 100 muscovites or 100 zircons, the cooling history that each individual grain experienced. So for, let's say, this curve here, most of this cooling history here are cooling ages between about 40 and 25 MA for a curve like this. So that means that out of 100 grains, let's say, some of them cooled at 40 MA, some of them at 30, some of them at 25, some at 35, and they sort of make a hump here, okay? So these different grains that cooled at different times ended up in the same sediment. So the cooling for argon muscovite is 400 degrees Celsius, let's say. So the top of the middle crust. So what's happening is rocks in the Himalaya are being brought up to the surface by a combination of tectonics and erosion. And when they finally get to the surface, on their path, they cool through 400 degrees Celsius, then they end up in a river, then they end up in the Siwaliks. Same with the zircon fission track, except that the cooling age here is more like 200, 180. So it's a lower temperature. So in both cases, we're tracking all of the cooling, the composite cooling record of the adjacent portion of the range where it dumps into the Himalaya. So what we generally expect in the model is that there's a lot of rapid uplift in the Western Himalaya early, and in the Central Himalaya a little later, and then the East Central Himalaya the latest. So that would suggest that the red lines here should have cooling earlier, and the blue lines here should have cooling later. And that's essentially what you see in the data. You see the red lines with a lot of cooling earlier, and the colder colors with a lot of cooling later. Now, there's a fair amount of visual bias in this that actually emphasizes my point more than it ought to be emphasized, because there's younger samples typically in the East and more older samples in the West. But when you correct for that by, say, just looking at the samples deposited at a 5 million year interval, it still shows the same pattern. You still have younger cooling ages in the East, or East Center, and you have older cooling ages in the West. Now, something else to point out is that this looks like a lot of data, but this is everything for the whole Himalaya. There's only about 6 or 7 sections represented here. It's really costly and really time consuming to generate this data. To generate this much cooling data for single samples is an immense amount of work. So there isn't actually that much data, and there's a potential that this is, with a lot more data, maybe it starts to see the pattern shift a little, but I think it's fairly robust. So yeah, in general, these are going to be showing you exhumation through the deeper sort of middle crust. This is closer to the surface. All of it, if you have rapid uplift followed by rapid exhumation, zippering from the west to the center, you should have the west cooling earlier and the center cooling later, the east cooling later, and that's what you see. So that is sort of consistent with, if you think the south Tibet attachment is shutting off, consistent with the rise in topography as it would be in this model, then it's earlier in the west, later in the east. Earlier in the west, later in the east. I hope that helps. Thank you for the question. All right, now
yeah, thanks, Alex. I think we have already closed the question checking from the chat, but there are a couple of questions which I received already. So can you just close the slides? Okay. There's one question from Diganta Kalita. So asking, want to know about the difference in intensity effect of volcanism during the detachment period in the central and western part.
I would say there's nothing new. In terms of the volcanism, people have been arguing that the volcanism, the atacitic and high potassium volcanism in South Tibet reflects slab breakoff and lateral propagation, lateral migration of slab tearing. If I can't recalling off the top of my head, the earliest reference is either 2010 or 2012, but I could be wrong. It's plausible that the French were on this even a decade earlier. I just don't remember from either the Grenoble folks or the folks at Lyon. I know the folks at Lyon were arguing this on the basis of metamorphism 20 years ago. The use of the atacitic volcanism migration from east to west and west to east to infer slab tearing is something where I am following others, and these ideas are at least a decade old, and there's been at least 5 or 6 papers over the last decade in which people have delineated this pattern and interpreted it in the same way.
Thank you. So there's one last question from participant. Is there any direct correlation between slab detachment and topography? If yes, why has it anything to do with isostatic compensation?
Well, I mean, isostatic compensation is just, it's just everything's weight, right? So if essentially the depth of compensation would get a whole heck of a lot lower if you put a big heavy slab below everything. And so that's gonna pull down on everything. And then if you release it or move it out of the way, then everything will bounce up. It's the same, so the same principle. I mean, what is isostasy, but it's a rubber ducky in a bathtub. And if you put lead running shoes on that rubber ducky, you put a lot of weight at the bottom of that rubber ducky, or put a backpack on him, he's gonna sink lower. You take the backpack off, take off the lead running shoes, it'll pop up. The slab is simply part of that weight budget. So we expect that if you remove the slab, if it was there and then you remove it, then you should have a topographic rebound. So thank you. I can't hear anybody anymore. Can you guys hear me?
Yeah, I can hear you.
Okay.
I think this issue with Dr. Basanta's internet. Dr. Basanta, can you hear us?
Well, I think he said that was the last question. Was it?
Yeah, I think, that was the last one.
All right.
So yeah, I think now, yeah, I don't think Dr. Basanta's net is gonna.
Now we all go back for tea and cake, right?
Well, thank you so much, Dr. Alexander. And
thank you very much.
Thank you for the wonderful insights on how the Mantle Dynamic guided the main phases of Himalayan Crustal Tectonics. The session was purely technical and was really informative, and I'm getting quite a good responses from our participants as well. So yeah, it was really good to know about the dynamics, and we'd also like to thank Dr. Basanta for his excellent moderations and making this session, webinar session, more lively. It is always pleasure hearing from him as well. So I believe this session has definitely added important insights to our understanding, and has been really important to all of our participants. The Q&A session was also really interactive with very healthy engagements and interesting questions. We tried our best to address all of the questions, and in case if you have any further queries, you can please feel free to mail us at info@inhrr.org, or also on the email address as Alex has provided. And I would also like to convey my big thanks to all of our organizing team, especially our speaker, Dr. Alexa Webb, session moderator, Dr. Basanta, and our distinguished guests and participants for participating in this session. We'll be sharing the recorded session on our YouTube channel, and the links will be forwarded to the registered email. So we have a long way ahead, and we would be really happy to collaborate and coordinate with the number of organizations to aim for the sustainable risk reduction. And before I end, I would like to share our scheduled webinar on DRR that will be hosted on August 8th. So it will be mainly related towards the geohazard risk assessment, and there will be two speakers. One will be one from the national side, and another will be the international speaker. So we will be having our session on August 8th. So we'll be also forwarding the links to all the registered emails. So with this, I would like to sign up from our session for today. Thank you, everyone. Namaste, and have a wonderful time. Namaste.
Namaste.